All right, welcome to our review for Calculus 2. Let's go ahead and get started with some multiple choice questions. So in the multiple choice section, what I'm looking for is smaller concepts. I'm trying to test smaller concepts that I think are not worth putting an entire problem on there. And I am going to probably shorten the actual exam from the practice final. I've kind of done things in chronological order too, that we learned them in the book. So first of all, we got a function cube root of 1/5 x plus 1, and we want to find f inverse. So remember that the way that you do this is we have set y equal to cube root of 1/5 x plus 1. Then you either want to switch x and y and solve for y, or solve for x and then switch x and y, either way. So if we switch our x and y here, then we've got x equals cubed root 1/5 y plus 1, and then cube both sides to undo the cubed root. So we've got x cubed equals 1/5 y plus 1. Bring the 1 over as a negative. So then x cubed minus 1 equals 1/5 y. And then multiply both sides by 5. And that 5 is going to get multiplied through here. So 5 times x cubed minus 1 parentheses equals 5 times 1/5 y. And these guys cancel, and so here you've got 5x cubed minus 5 is our y. So right there, B. Let's see here. I'm just testing properties of logarithms. So remember, subtraction outside is division inside, and then exponents will factor up and down inside exponents. So the first thing we're going to do is bring this 2 up on top here. So this will be equal to log base 3 x plus 2 squared minus log base 3 of x minus 2. And then again, subtraction outside is division inside. So this is going to be log base 3. And this is log of the top minus log of the bottom. So x plus 2 cubed. Squared. X plus 2 squared. And I better erase that guy. Over the denominator x minus 2. And that's this guy right here, a. Derivative of log of a function. So remember, what you do is you put the function on the bottom and its derivative on the top. So this is log of a function g, and the derivative formula is that that's g prime over g. So I want to do g prime over g. So our inside function g is 4x cubed minus 1. And then the derivative of that, 3 times 4, 12x squared upstairs. And derivative negative 1 is 0. So that guy's out, that guy here, a again, right there. Let's see, number 4, I had an extra number in there by accident. Number 5, derivative of e to a function. So this is going to be e to the function, x squared plus 1. And since it's e to a function, you've got to multiply by the derivative of the inside. So times 2x. So C right there. So testing some simple derivative formulas, integral formulas. What trig substitution would you use here? 25 plus x squared? Well, remember your trig identities are 1 minus sine squared is cosine squared. 1 plus tangent squared is secant squared. And then secant squared minus 1 is tangent squared. So this thing looks like 1 plus tan squared theta. Okay, but we've got a 25 up here instead of a 1, so we want to multiply through by 25. So it's 25, this will be 25 plus 25 tan squared theta. And then the 25s here match up, so the x squared has to match up and be 25 tangent squared. So take square root, square root of 25 is 5, square root of tangent squared is tangent, so it'd be 5 tangent theta. So actually this guy should not be here. So that 2 should not be there. And it should be B, 5 tan theta. Okay, moving on. Find the best substitution for the integral. So remember, what you do is you write these as fractional exponents. So this would be integral, and this is going to be a rationalizing substitution because we've got these different roots with different indices. So it's going to be a rationalizing substitution, rationalizing U-substitution. So x to the 1/3 on top, and then downstairs we've got x plus x to the 1/4 on the bottom, dx. And what you want to do is find your LCD between 1/3 and 1/4, which is 12. And it's u equals x to 1 over the LCD, 1/12. So B right there. Okay, and then we've got a limit, and this involves powers and exponentials. So you could rewrite this as limit x approaches infinity, and we could bring the x to the -2 down on the bottom as a +2. So this is e to the 3x on top over x squared on the bottom. So then we've got exponential versus a power here, but remember that x squared is much less than e to the 3x. E to the 3x grows a lot faster. So the top's getting bigger faster. Both of these things are positive. This guy's going to plus infinity. And then let's see here. This was L'Hopital's rule if we actually wanted to do the evaluation, because it's form infinity over infinity, indeterminate form. So if we needed to go, if this was in the problem section, you'd use L'Hopital's rule. Here, limit as x goes to 0, log 5x over sine x. Okay, so this is form 0 over 0. Oh no, I'm sorry. X approaches 0 plus log of 5x. Remember that the log function looks like this. I'm thinking log of 1 is 0. Your log function looks like this. And this goes down to minus infinity. That's ln of x, and also ln of 5x is just going to be a little bit different. It's going to be horizontal stretch because you've got a multiplication factor inside, actually horizontal compression. So let's see, so this guy up here is approaching minus infinity. So this is approaching minus infinity. And then as x approaches 0, sine of x also approaches 0. So this approaches 0. And if you think about, well, is it going to come from the positive side or the negative side? Well, x is approaching 0 from the positive side. Graph of sine of x looks like this. Okay, so x is coming in like this, so your y value is coming down, sine x is coming down from the positive side. So sine x is approaching 0 from the positive side. So this is infinity, negative infinity makes the top big negative. The bottom is approaching 0. That also makes the bottom of the fraction is smaller. The ratio gets larger. So both of these things are making the ratio larger, and it's a negative over a positive. So this is going to be minus infinity, which is a. Integral x e to the x squared. This guy's just an easy U-substitution. I see x squared there and x there, so we need a 2 in here and a 1/2 on the outside. And then we're ready to do u equals x squared, and your du then is going to be 2x dx. So 2x and dx is your du, and then this is your e to the u, so this is 1/2 out in front, and this is going to be integral e to the u du, which is just 1/2 e to the u plus a constant. And plug our x squared back in, and this is going to be 1/2 e to the x squared plus a constant, which is d. And then last we got a series, converge, diverge, which test? Okay, well, let's see. This is powers, exponentials, and factorials. And we know that the n is much smaller than the 7 to the n, the exponential, which is much smaller than the factorial. And we've actually seen some examples like these. Even when you multiply a power and an exponential together, it doesn't get bigger than a factorial. Okay, this grows a lot faster even than that product. So the bottom's getting bigger faster. That makes the general term go to 0 really fast. So this guy's going to converge, and then that would be a ratio test. So powers, exponentials, and factorials, and n to the n, which is a generalized, well, not a generalized exponential, but a sort of a generalization, because you got a variable base and a variable exponent. Those kinds of things are asking for ratio test. Arc length of y equals natural log x squared plus x cubed from 1 to e 1 plus e cubed. So here I'm just saying state the integral. I probably would do this as a multiple choice here, but remember that arc length here is the integral from a to b square root 1 plus f prime of x squared dx. So integral, we're using x values here, so it's going to be x equal 1 to x equal e, and then square root, we don't have to do any simplifying here, 1 plus, and our f prime, derivative of natural log of x squared. This is an outside exponent. So this is a function to a power. So the 2 comes down times ln x, and then this is first power, which we don't have to write the 1, and then times the derivative of the inside function, which is 1 over x, inside function's log, and then plus the derivative of the second term, x cubed, is 3x squared, and that whole thing gets squared, and then that's dx. Okay, and then next here, if you have a simple calculator and you need to evaluate a definite integral that you can't find the antiderivative of, what can you do? Well, this is, if you can't find the antiderivative, then it's a definite integral here. So you can find an approximate integral. So you could use, you know, things like left-hand rule, or, you know, trapezoid rule, some type of an approximate integral. Is what I'm getting there. If you can't find the antiderivative and it's a definite integral, you can always approximate. Okay, and moving on down the way here. So here, eliminate the parameter. So you got parametric equations in x and y. And remember, what you want to do here is you want to solve one equation for one variable and substitute it into the other equation. So let's see here. We could solve, it's actually a little bit easier here to solve for our y than it is to solve for our x. So let's see here. Yeah, it's a little easier to solve for y than it is for x, because if you solve for x, then you've got to take some square roots. So why don't we go ahead and solve y for t, and then we'll plug into x. So we'll actually end up getting x in terms of y. So let's see here. So we want to bring the root t over on this side and the y on this side. So square root of t comes over as a positive, this y comes over as a negative, so 1 minus y. And then we'll square both sides. And this square and square root will cancel out. So we get t equals the quantity 1 minus y squared. And then we can plug that in here. So then our x is going to equal 2, well actually, yeah, 2t squared. Okay, so 2 times t squared, and our t is 1 minus y squared. So 1 minus y squared, and then that gets squared. So x is going to equal 2 times 1 minus y to the 4th power. And now this is x in terms of y, but that's okay, we've still eliminated the parameter. Find a point on the graph where you've got a vertical tangent. Remember that dy dx equals dy dt over dx dt. So you want a vertical tangent, that's going to be when the bottom here, dx dt equals 0. So dx dt is equal to 2t, and we set that guy equal to 0, so divide both sides by 2, so that tells us that t equals 0. And if t equals 0, then that's going to give us a point in xy coordinates. So then x is going to equal 0 squared minus 1, which is negative 1, and y is going to equal 2 times 0, which is 0. So negative 1 comma 0. And you could verify that by graphing this on your calculator too. Which of the following is a graph of? So this is basically be a calculator question, e to the 1 over x squared. So you know, just a graph identification question. And you know, this one's in y and x, but you know, you should know how to graph in polar coordinates and also parametric coordinates, or parametric equations, excuse me. What U-substitution would you use to evaluate this integral? Well, let's see, I've got log of cosine 2x times sine of 2x over cosine 2x. So I've got log of a function. I'd like to reduce this down. So I'm thinking, let's see, if I let my u equal cosine of 2x, then this would be u here, and this would be a u down here, and your du would involve a sine 2x, which is on the outside. So that looks like that would work. So it looks like u equals cosine 2x would work, because then your du would equal derivative of cosine's negative sine 2x, and then times the derivative of the inside, which is 2. So negative 2 sine 2x. So this would be a u down here. This would be a u. and then this would be part of your du. Actually, I guess we'd need a -2 in there and a -1/2 on the outside. But yeah, this would be part of the du. So you'd have a little bit of multiplying to do. But yeah, everything would work out fine there. So just identifying a substitution. The integral that gives the surface area of. Okay, and those are parametric equations. So remember that. Oh, and then we have to revolve around an axis. So actually, I need to give you an axis. So let's see. Let's revolve around the y-axis. And then we can write an integral there. So if you're revolving on the y-axis, then your surface area is going to be the integral from alpha to beta, starting and ending coordinates, and then I'm starting and ending parameter values, because everything's in t here, and then it's going to be 2 pi x, and then this times ds, which is your square root of dx dt squared, plus dy dt squared. Oops. Dt. So, and remember, when you're revolving around the y-axis here, you've got some equation, you're revolving around the y-axis, that the radius is going to be an x-coordinate, and that's what this is. This is your radius. Just 2 pi r ds. So, let's see. If we've got to get our parameter values. So x equals 0, which is saying t cubed equals 0, so that's going to be starting at 0, to 1, so t cubed equals 1, cube root of 1 is 1, so this is 0 to 1, 2 pi, our x is t cubed, and then square root, dx dt is 3t squared, and that guy gets squared, plus dy dt is just e to the t, and that gets squared, dt. And then the only difference if you were revolving around the x-axis is this would be 2 pi y, because then if this is the graph, well, yeah, if you're revolving around the x-axis, then you'd have some graph like this, and your radius would be a y as you're revolving this guy around here, like this. So your radius is a y, whereas here your radius is an x value. Another U-substitution, we're integrating cosine squared 2x, sine to the 5th 2x. So up here this was a straight U-substitution. Well, actually we could have done 2 U-substitutions, could have got rid of the 2x to start with. But here this is powers of products of sines and cosines. So here we've got an odd number of sines, so you're going to break one of those off to be the du, and then your u is going to be the cosine. Okay, so here we've got an odd number, so we break this up into sine to the 4th 2x times sine 2x, and then this is going to be your du, except for maybe doctoring up with sines, and then your u is going to be right here. Well, this will actually be u squared. Your u would be cosine 2x, so this would actually be u squared. And then remember, if you wanted to go further, what you do is you write this as sine squared squared, sine squared 2x squared, and then you write each one of these as a 1 minus cosine squared. 2x. And that gets squared. So this would be 1 minus u squared squared. So you got a u squared, you got a 1 minus u squared squared, and then this is part of your du. But again, du would actually be negative 2 sine 2x. So you have to multiply by negative 2 and then a negative 1/2 on the outside here. So giving you just a little extra, more than what you need there. All you really need for this one is that right there. Okay, and moving on down the line. What is the form of the partial fraction decomposition? So the form of the decomposition is just the general form here. So let's see, we've got repeated linear factor. So the decomposition is going to have an x in the bottom and then also an x squared. Because remember, you get since this is an x squared, you get 2 terms in the decomposition. If it was an x cubed, you'd have 3 terms. So this would be plus a b over x squared. And then this is an irreducible, non-factorable quadratic here. So for that one, you've got your x squared plus x plus 1 on the bottom. And then on the top, you're going to have a linear factor. So it's cx plus d. So, and then, remember what you do, in general, if you had to work out the a, b, c, and d, you'd set these guys equal, multiply through by this LCD, and then you get an equation without any denominators in it. And then you could either plug in x values that made factors cancel out, zero out, or you could multiply everything out and set the constant coefficients equal, set the x coefficients equal, set the x squared coefficients equal, set the x cubed coefficients equal. And that's usually what works better when you've got a quadratic. Alright, on to the problem section. So here we're computing a limit. We've got an e to the negative 2x and a log 3x. X is going to infinity. So this piece is approaching 0. And then as x goes to infinity, log 3x approaches infinity. So this is 0 times infinity. That is an indeterminate form. So it's asking us for L'Hopital's rule. So first we have to change it to 0 over 0 or infinity over infinity. So let's bring the e to the 2x, e to the negative 2x down as a e to the positive 2x. So this is limit x approaches infinity. We'll keep our ln 3x up on top. And then bring the e down on the bottom and change the sign on the exponent, so 2x. And now this is infinity over infinity, so we can use L'Hopital's rule. So derivative of the top and bottom separate, so this will now be limit x goes to infinity, derivative log of a function, and put the function on the bottom, and then its derivative 3x is 3, which is on the top. And then derivative e to the 2x is e to the 2x times the derivative of the inside function, so we need it times 2 here. And let's see, these 3's will cancel and leave us a 1 over x up on top. And this is actually 2e to the 2x over 1 on the bottom. So if we invert and multiply, we get limit x goes to infinity. Always simplify before you decide what the form is. We'll have a 1 over x and then times, invert this guy, so it would be 1 over 2e to the 2x. So this is then just limit x goes to infinity and multiply those fractions straight across. So this is 1 over 2x e to the 2x. Both of these things are going to infinity on the bottom. This is form number on the top over infinity on the bottom, and number over infinity is a determinate form. This guy goes to 0. Okay, next up we are evaluating an integral. I look at this and right off I see a log x and then dx over x is the derivative there. So I'm looking at this thing and I'm thinking we should probably start off by using a U-substitution. That's always your your first method that you try, in addition to simplifying the integrand. But u equals ln x, so then du, it's going to be 1 over x dx. So here's our du here, and then this is 1 plus u squared. So this would be integral du up on top, and on the bottom, square root 1 plus u squared. And now this is when you got square root of sum or difference of squares underneath there, then you're looking at a trig substitution, and this one looks like 1 plus tan squared theta. So the ones already match up, so the u squared is tan squared, so we're gonna use u equals tan theta here. So I'm doing a trig sub, get some practice with trig substitutions. U equals tan theta. Then our du, derivative of tangent, is secant squared. So this is secant squared theta, d theta. And the 1 plus u squared is 1 plus tangent squared. So this is going to be integral. Up on top we've got our secant squared theta d theta. And then downstairs we've got square root of, we know it's 1 plus tan squared, that's the way we set up the substitution. And 1 plus tangent squared is secant squared. So this is integral secant squared theta over square root secant squared theta d theta. And then the square root and the square cancel each other out, so we just got a secant theta on the bottom. So this is integral secant squared over secant. And this secant cancels off one of those guys, so we're just doing the integral of secant theta d theta. And this is one of the ones that we use a formula for, and you know, if this were to come up I would give you the formula on the exam, but this is the one that turns out to be natural log absolute value secant theta plus tan theta. And then this is indefinite integral, so we need a plus c on there. Okay, so now we get to change back to x's. So remember, you go back to your substitution, u equals tan theta. So when we draw a right triangle here, okay, and we know that tan theta equals u, which we'll write as u over 1, and this is opposite over adjacent. So let theta be this angle down here. The opposite side is going to be u. The adjacent side is 1. So this up here is going to be square root of a squared plus b squared. So 1 squared is 1 plus u squared. And then notice that this root 1 plus u squared, that occurs right here in the denominator. So we know that we've done this substitution correctly. And so now we need natural log, absolute value, and secant theta. Secant is 1 over cosine. Cosine is adjacent over hypotenuse. So here we want hypotenuse over adjacent. So root 1 plus u squared over 1. So this is just root 1 plus u squared. And then tan theta is u. So plus u. And then close the absolute value plus c. And then all we have to do now is put our natural log x back in for u. So this then equals natural log absolute value root 1 plus ln x quantity squared, and then plus ln x absolute value, and then plus c. And we got it. Alright, got another integral here. This is power times an exponential. So that guy is asking us for integration by parts. So we need to get a u here and a dv. And remember, u, we want to have a simpler derivative, and dv easy to integrate. Well, if you differentiate x, you get a simpler derivative. If you differentiate e to the 2x, it's basically e to the 2x times 2, which is about the same. And dv, well, both of these are easy to integrate, but if you integrate this one, it doesn't get more complicated. Here, you get an x squared over 2, so you're increasing the power. So we want to let u equal x, and our dv is going to be e to the 2x dx. And then let's see here, du, then derivative of x is 1 dx. And then here v, you do the antiderivative of e to the 2x, you get e to the 2x. If you're doing a derivative, you do times 2. With antiderivative, remember you do 1/2. And then we want uv, so this integral is going to equal uv minus v du. So u times v is going to be 1/2 x e to the 2x minus integral v du, which is 1/2 e to the 2x, and then our du is just dx. And then this 1/2 we could pull on the outside, and then the antiderivative of e to the 2x is going to be another 1/2 e to the 2x times the 1/2 that's already there is going to be a 1/4. So this is 1/2 x e to the 2x, and then minus 1/4 e to the 2x, and then this is indefinite integral, so we need a plus c on the end. So, I'm going to pick, maybe 1 or 2 integrals. I'm doing like 1 or 2 problems from each chapter. And so from the integration chapter, do a couple different methods. So you want to go back over, those practice exams and just kind of review the different methods, or, go over the video. Okay. And now I got a differential equation to solve. And the only method that we had was separation of variables. And so let's see here. What we want to do is we want to get all of the y's on one side and all the x's on the other. Now our dy is on the top on the left, so we want to get our y's on the left hand side and then get our x's over on the right hand side, and then we'll plug in this to find our constant. So let's see here. So we've got a negative dy over dx equals 2 minus x over xy. And let's see here. I want to multiply both sides by dx, and then I want to have a positive dy here. So let's multiply both sides by negative dx and times negative dx. And then this will cancel, and then these two negatives will make a positive. And then let's see, to get the y's over on the left, I just need to multiply both sides by y. And so I'll have y dy on the left hand side. And then on the right hand side, these guys cancel. This negative, let me multiply it in times 2 minus x. So that'll be negative 2 positive x. So that's going to be x minus 2. Still got an x on the bottom. And this negative is incorporated in here, and then we got a dx out there. So now we've got our variables separated, so now we can integrate both sides. And on the left hand side we get y squared over 2. And on the right hand side, well, let's see here. we want to rewrite this guy. Let's split it apart over the LCD here. X over x is 1 minus 2 over x. And do that integral. So the integral of 1 is just going to be x. And then the integral of 2 over x, well, we can take the minus 2 out in front, and the integral of 1 over x is natural log of absolute value x. And then we combine we get a plus c on both sides, but remember we combine those on the right hand side. Okay, and then this is an implicit solution. We'd like an explicit solution if we can get it. And you know, it's not that big of a deal here. So let's multiply both sides by 2. Excuse me. So this whole side gets a times 2. And these guys cancel. So we've got y squared is 2 times x, 2x, minus 4 ln absolute x, and then plus 2c. But remember, this is an arbitrary constant of integration, so when you multiply that 2 in, 2 times c, we could just rename this constant if we wanted to 2c and call it c1, but we'll just leave it as a c here. So here our arbitrary c, it absorbs multiplication by constants. You probably remember some of the problems that we were working with, and we were renaming the constants, so you can do the renaming. That was sometimes when we had logs on both sides and we had to exponentiate both sides. Okay, and then we're going to take square roots on both sides. And so we get y equals, and there's a positive and a negative square root. And this is going to be 2x minus 4 natural log of x, and then plus c. So that would be an explicit solution, and this actually is not a function because of the plus or minus in there. And then we've got, let's see here, we've got an initial condition. Y of 0 equals 1. And let's see here, y of 0 equals, y of 1 equals 0, so x is 1 and y is 0. So this is essentially the point 1 comma 0. This is your x, and this is your y. And here, y equals plus or minus, well here y equals 0. If the y was positive or the y was negative, then we could rule out and say which one of these guys we wanted to use. But here, since our y equals 0, we'll keep that plus or minus in there. So plug in y equals 0 equals plus or minus square root, and then plug in x equals 1. So this would be 2 times 1 minus 4 natural log absolute value of 1 plus our constant, and this guy is 0. Log of 1 is 0, so this all zeroes out, and so this is equal to plus or minus square root 2 plus c. So if we squared both sides, we get 0 equals 2 plus c. Because if it's a positive or a negative, you square it, you're going to get rid of the negative. 2 negatives make a positive, 2 positive make a positive, and then you'll get rid of the square root. So bring this over, then c equals negative 2. So our final answer here, we do y equals plus or minus square root 2x minus 4 ln absolute x, and then for our plus c, put in a minus 2. Okay, so that's the solution that goes through the point 1, 0. And again, this is, this is not a function. Y is not a function of x because of the plus or minus. But that's an explicit equation for the solution. And up next, an improper integral. Ooh. Things are getting really exciting now. I'm having trouble containing myself. Let's see, hint, take it one piece at a time. Well, this 1 over x cubed, if you graph that guy, x equals 0 is a 0 for the denominator, and 1 over x looks like this. 1 over x cubed looks just about the same. Very similar. It goes up to infinity at 0, and then it tapers off to 0 at infinity. And we're going from 0 to infinity, so we essentially want to find the area under this piece here. So we've got two trouble points, one at 0 and one at infinity. So we want to break this guy up. So the integral from 0 to infinity of 1 over x cubed dx equals, and we can break it up at any point we want. Probably x equals 1 is the easiest one to do. So 0 to 1, 1 over x cubed dx plus integral 1 to infinity 1 over x cubed dx. And then in order for this integral 0 to infinity to have a value, both pieces here have to be finite. Now this one here we know is finite by the p-test. Okay, so we know that one's finite. So so just notice here that this guy here, this is finite by the p-test. For integrals that we learned in that section. So so that one's finite. But this one, we're not sure. So why don't we try that one first, because if this is infinity, well then the whole integral diverges. So let's work on integral from 0 to 1 of 1 over x cubed dx. And our trouble spot is down at 0. So remember, we change this into a limit, and we do integral from a up to 1 and let a approach 0 from the plus side. And 1 over x cubed dx. Okay, this isn't a hard integral, that's x to the negative 3. So this is limit a approaches 0 from the plus side, integral of x to the negative 3 dx, and this guy is from a to 1. So we raise the exponent, divide by the new exponent, so that's going to be x to the negative 2 divided by negative 2, which we could write, we can bring the x squared down on the bottom. So this will be negative 1 over 2x squared is going to be our antiderivative here. So in my next step, so just parenthetically, just figuring that out, save us a little bit of writing here. So this will be limit a approaches 0 from the plus side, and now our antiderivative is negative 1 over 2x squared, and we're going from a to 1. Okay, so limit a approaches 0 from the plus, and we want to plug a 1 in here, so we get negative 1 over 2 times 1 squared minus, and then plug an a in there, negative 1 over 2a squared. Okay, so let's see, so double negative here makes a positive. This is just negative 1/2. A is approaching 0, so this is a form number over 0. And the top is positive, and the bottom is also positive because a is approaching 0 from the plus side. So, well, actually it wouldn't matter because a squared is positive. So this is number over 0, and it's positive over positive. This piece is approaching plus infinity. Okay, so this guy here is approaching infinity. So you got negative 1/2 plus infinity. This is infinity. So even though this piece was finite by the p-test, since this piece is infinite, the integral diverges. So since the integral from 0 to 1 of 1 over x cubed dx diverges, the whole integral from 0 to infinity of 1 over x cubed dx diverges. Okay, and next up we have a centroid. So centroid of a region bounded by y equals 2 minus x squared and y equals x squared. So this is a region between two functions. So one of the first things you want to do is graph your region on the calculator. So let's see here, get this guy going. Y equals x squared, just a parabola here. And then 2 minus x squared, so this is x squared tipped upside down, shifted up 2. So that guy's going to look like this. Okay, we want the centroid of that region. This is x squared, and this guy is 2 minus x squared. Okay, well, this is area between functions here. And one of the first things that you want to do is look at symmetry and see if you've got any symmetry. And the y-axis is a line of symmetry. Divides this guy in half. So this is the y-axis. This is x. The y-axis divides this in half. So x equals 0 is a line of symmetry. So that implies that the centroid's on x equals 0, so x bar equals 0. And then I just noticed this, but it looks like we got another line of symmetry right here. And so if we find those intersection points, that should be a line of symmetry, and that would give us the y-coordinate. But just for practice, why don't we go ahead and figure out our y-coordinate, and then we'll try and confirm it here with this second line of symmetry. Okay, so our x bar, remember, if we needed to figure it, it would have been 1 over the area, and then integral from a to b, and if it's just one function, it's x f of x. But for between two functions, for a region between two functions, it's x f of x minus g of x dx. Okay, we didn't need that one because we had that line of symmetry. And our y bar is 1 over area. And then we do integral, and it's usually just 1/2 f of x squared, but since we've got region between, this is going to be 1/2, and it's going to be f of x squared minus g of x squared dx. And for both of these, this is the top function minus the bottom. And then this is top squared minus bottom squared. So our top function is 2 minus x squared. Our bottom function for that region is x squared. Okay, but first we need our area. Okay, so let's see where these two guys hit. So let's see. So if we set x squared equals 2 minus x squared. Let's see, bring this x squared over as a positive. So 2x squared equals 2. Cancel 2 off both sides. X squared equals 1. So then x is going to be plus or minus 1. And then our area then is going to be the integral of top minus bottom. So integral from -1 to 1 of top function minus bottom function. So that's going to be 2 minus x squared minus x squared. dx. So again, this is top minus bottom. And that's just going to be 2 minus x squared minus another x squared. This is just integral from -1 to 1 of 2 minus 2x squared dx, which is an easy antiderivative. That's going to be 2x minus 2, and then this will be x cubed over 3. And actually, well, -1 to 1, we could have used symmetry to find that area, couldn't we? Could have gone 0 to 1. That's okay. And we'll go -1 to 1 here. So if you plug in a 1, you get 2 minus 2/3. So 2 minus 2/3 minus, and if you plug in a -1, you get a -2 minus, and then this -1 cubed gets another negative, so this will be plus 2/3. And so that's, if you do the calculator work here, you'll get 8/3. That's 8/3 area. So this piece here, 1 over a, is going to be 3/8. And then we're doing integral, well, this is integral a to b here. And our integral is -1 to 1. And our f of x squared, that's our top function squared, so this is a 2 minus x squared minus bottom function squared. So that's x squared dx. Okay, so we got a little bit of algebra to do, so we got to FOIL this guy out. So let me do some of this algebra just below here. So this is 2 minus x squared times 2 minus x squared. And then x squared squared is x to the 4th, so minus x to the 4th. So first terms, this will be 4. Outer terms -2x squared. Inner terms -2x squared, so minus 4x squared. And negative times negative is going to be a positive. X squared times x squared is x to the 4th. And then minus x to the 4th. So those guys cancel out of there. So we were just integrating 4 minus 4x squared. So this is going to equal 3/8. And then integral -1 to 1, 4 minus 4x squared dx. And that's not a bad antiderivative, so this is 4, whoops, you needed 3/8 out in front. And then this will be 4x minus 4, antiderivative x squared is x cubed over 3. And then we are going -1 to 1. Alright, so now we just have to do our plugins here. Oh, you know what? I forgot my 1/2 here. Right there. There should be, let's see if we bring that 1/2 on the outside here. Then we'll put it out here. And then this 3/8 here would actually be 3/16. So just change that to a 3/16. Okay, so get rid of 3/8 here and 3/8 here. Yeah, you guys probably noticed that. We're yelling at the screen. You're laughing at me again. I know you're laughing at me. Cut it out. Pay attention. Yeah, you're probably sitting on the couch with a big gulp holder and a can of popcorn watching me do this, aren't you? Well, just better pay attention here. So 16 and a 16 right there. Yeah, you're saying, yeah, you better pay attention. You're the one that made the mistake. Okay, so 1 goes in on each piece, so you got a 3/16 out in front. And let's see, 1 goes in, so 4 times 1 is 4, minus 4 times 1 cubed over 3, so 4/3. And then minus, and let's see, -1 goes in, so 4 times -1, it'd be a -4. And then minus, and this negative 1 cubed will give another negative, so it would be plus 4/3. Okay, so then let's see here. This is 4, and this double negative is going to make another 4, so this is going to be 8. Negative 4/3, and then this negative with that one is going to be another negative 4/3, so 8 minus 8/3 is the inside there, which is equal to, let's see, this is 24/3 minus 8/3 is 16/3. So that's the inside of the parentheses that I'm evaluating. So this is equal to 3/16 times 16/3, which equals 1. So our y bar is 1. So x bar is 0, y bar is 1. So we've got 0, 1. And that does agree here with what our dotted line of symmetry was, because this intersection point right here, that's at 1, and this is at negative 1. And if you take 1 and put it into x squared, this line is going to be at height 1. So this is actually y equal 1. Okay, well that's good that this agreed with our symmetry. So that was good practice. Now you don't have to do all this out if by chance, you see 2 lines of symmetry on the exam, which isn't going to happen, but you might see one of them. By all means, use symmetry. Alright, and we are getting there. Okay, let's take another look at this problem here. What we want to do is just get rid of that minus sign. Okay, this will have the exact same graph as we had before, except it's going to be opposite orientation. So let me get my pen back here. So in other words, we just want to change that to a plus. So this is going to be 1, positive 1 minus cosine. So if you graph these guys here, the r equals cosine theta is a circle along the positive x-axis, diameter 1. So it looks like this. And then this 1 minus cosine theta cardioid, it hits at 1 and negative 1 on the y-axis here. And it hits at negative 2 on the x-axis. Okay, and we've still got this small piece here that I want to blow up. So we've got the cardioid coming up like this. So this is our 1 minus cosine theta. And then we've got the circle coming like this. So that's our cosine theta. And again, we want to find the area enclosed here and the area here. By symmetry, those two are the same, so we're just going to find this area here and double it. Okay, so first we have to find this angle right here, and 1 minus cosine theta and cosine theta, these guys are both oriented counterclockwise. So when we find the angle, the same angle will be given this point rather than an angle that's pointing the opposite direction, because you don't have the negative radius to deal with. So we set 1 minus cosine theta equal to cosine theta, and let's see here, bring this cosine theta over as a positive, so 2 cosine theta equals 1. And so divide both sides by 2, so cosine theta is equal to 1/2. And so then your theta is going to be pi over 3 or 5 pi over 3. and we're interested in pi over 3. So this angle is pi over 3. So let's label these like we did before. This area we're going to call A1, and this area here we're going to call A2, and our total area is going to equal 2 times the sum of two integrals. So for area 1, if we draw a radial segment here from the origin out to a point on here, so it looks something like that. The limiting positions of that radial segment are here at pi over 3, and then as this point approaches the origin, the radial segment rotates around and it gets closer and closer to tangent position that's parallel to the y-axis. So in other words, this angle here is 90 degrees when you're right there at the origin. This circle is tangent at the origin. So our first integral is going to go from pi over 3 to pi over 2. And area is the integral. Remember here that area is the integral of 1/2 r squared d theta. And so this is going to be 1/2, and our r on area 1 is cosine. So this is going to be 1/2 cosine squared theta d theta, plus, and then the second integral, the cardioid, when it comes down here, we've got a horizontal tangent there. So the starting angle is 0, and then see if we draw this radial segment from here to a point that's on the cardioid, get a radial segment like that. When that point is up here, the radial segment is close to being in the pi over 3 position, and as that point slides down here closer to the origin, then our radial segment is closer and closer to the x-axis, which is angle 0. So this is going to be 0 to pi over 3. Oh, vertical here. I'm looking at this. That's not pi. It's pi over 2. Sorry. Vertical tangent is angle pi over 2. And then this is 0 to pi over 3. And then we're doing 1/2. And then here our radius is on 1 minus cosine theta. So this is going to be times 1 minus cosine theta. And that guy gets squared d theta. Okay, so that's our integral. And then I get you started on evaluating these guys. So this 2 here will cancel. We can multiply the 2 in and it'll cancel out these 1/2s here. So we want to do the integral of cosine squared. So pi over 3 to pi over 2. And even power of cosine, we're going to use the half angle formula and do 1/2 1 plus cosine 2 theta d theta, and then plus integral 0 to pi over 3. And then this, we've got to FOIL this out. 1 minus cosine times 1 minus cosine. So 1 minus cosine and 1 minus cosine. Come on, pen. There we go. So first terms are going to be 1. Outer terms minus cosine, inner terms minus cosine, so minus 2 cosine theta. And last terms plus cosine squared. And this is d theta. Okay, so this guy we can bring the 1/2 on the outside. And we know how to integrate this. Integral 1 is going to be theta, and integral cosine 2 theta is sine 2 theta, and then with a 1/2. So this is plus 1/2 sine 2 theta. And we are going from pi over 3 to pi over 2. And then plus, we got a little bit more work over here because this guy we need to change into another 1/2 1 plus cosine 2 theta. So let's see, I think we have room for that in there. So this is going to be integral 0 to pi over 3. I got a 1 minus 2 cosine theta. And then plus, we get a 1/2 and 1 plus cosine 2 theta d theta. Okay, and then this guy we've just got to do the plug-ins on. So this is going to be a ditto plus, and then this guy we've got a 1 and we've got a 1/2 right there. So 1/2 here plus a 1 is going to be 3/2. So when we integrate that, that's going to be 3/2 theta. And then the integral of negative 2 cosine theta is going to be minus 2 sine theta. And then the integral of, this is a 1/2 cosine 2 theta, is going to be plus, if you integrate cosine 2 theta, here remember we got 1/2 sine 2 theta, and then we've got this other 1/2 coming in, so that's going to be 1/4 sine 2 theta. And then we're going from 0 to pi over 3. Okay, and then you just got to plug in. And I will let you do that part. So this is a lot cleaner here because we didn't have to worry about negative radius that we would have gotten up here. Alright, so hope that is helpful. So what we do is we set L, which is the limit, as n goes to infinity of absolute a n plus 1, so n plus 1 term over the n term, which is limit as n goes to infinity. Everything is positive here except the absolute, except when you take absolute value, the x minus 2 is going to stay in there. So, well, in the n plus 1 term, we'll have an n plus 1 on top, and then we'll have an x minus 2, n plus 1, and then down here we'll have a 5 to the n plus 1, and then all over n x minus 2 to the n over 5 to the n, and that whole thing gets absolute values. And then we invert and multiply, and again the only thing that's going to be left inside the absolute values is the x minus 2, because that's the only thing that could possibly go negative. So we've got an n, I guess I should put this guy in parentheses, n plus 1 up here, and absolute x minus 2 to the n plus 1, and then we're dividing by 5 to the n plus 1, and now multiply by the reciprocal here, so times 5 to the n on top, and on the bottom we've got n and absolute x minus 2 to the n. So these n5s will cancel out all of these except for 1 5. X minus 2 to the n, it's going to cancel all of these except 1 x minus 2, and then we got left our n plus 1 over n. So this equals limit as n goes to infinity, and we've got n plus 1 up on top, and an absolute x minus 2. And then on the bottom we've got a 5 left and an n, so 5n. Absolute x minus 2 is independent of n, so that can come out. So this will equal absolute x minus 2. And then take the limit as n goes to infinity of n plus 1 over 5n. Dominant terms are n and 5n. So if we get rid of our plus 1, this is just 1/5. So this is going to be 1/5 absolute x minus 2. And then we set that less than 1 to get convergence. So multiply both sides by 5, and we get absolute x minus 2 is less than 5. So as a between inequality, that's x minus 2 is between 5 and negative 5. And then add 2 all the way across. So negative 3 is less than x is less than 5. Okay, so that's the start of our interval of convergence, and then remember you have to go back and you have to check the negative 3 and the 5 individually. So x equals negative 3, plug that in right here, well actually right here, and you're going to get summation n equals 0 to infinity, and we've got an n up on top, and we've got negative 3 minus 2, so that's a negative 5 to the n. And then down on the bottom we got a 5 to the n. And so negative 5 over 5 is just negative 1, and that's got an n power on it. So this 5 will cancel the 5 out of there and leave a negative 1, or these n 5s will cancel the n 5s out of there. So this is just summation n equals 0 to infinity. And we got a negative 1 to the n right here, and then times n. But this is an alternating series. Here's our general term right here, the n. This is our b sub n, and that equals n. And we need that to go to 0, but as n goes to infinity, this goes to infinity. So this guy diverges. So that one's no good. That's not going to get included. And then if x equals positive 5, plug that in, we get summation n equals 0 to infinity. And now this is 5 minus 2. So this is n, and then this will be 5 minus 2 to the n over 5 to the n. So this is going to be summation n, and this is 3 to the n over 5 to the n. Oh, no, what am I doing here? Let's see. I added 2 all the way across. Sorry about that. I forgot to add my 2 here. This is a 7. And this is actually going to be a 7. That's a 7. 5 plus 2. Add 2 all the way across. So this is 7 minus 2, which is 5 to the n over 5 to the n. These guys cancel. This is just summation of n from n equals 0 to infinity, and that guy diverges too, because terms don't go to 0. Here terms go to infinity, which is not equal to 0. Okay, so both of these pieces diverge. So your interval of convergence then does not include either of the endpoints. it's negative 3 to 7. Okay, and then the radius of convergence, again, here you've got an interval from negative 3 to 7. Negative 3, negative 2, negative 1, 0, 1, 2, 3, 4, 5, 6, 7. So that's your interval of convergence, and then your 2 should be right in the middle. So negative 2, negative 1, 0, 1, 2, 2 right there. So your radius of convergence is 5, which is the distance between 2 and 7, or between negative 3 and 2. So your R equals 5, because this is 10 units wide, and so the radius is 5. So there's interval and radius of convergence. Okay, and then the last one, find a Taylor series. Okay, so what you want to do here is start finding derivative values here, because remember your Taylor series, give ourselves a little bit of room here, but your Taylor series, t of x, is defined to be the power series given by summation n equals 0 to infinity, and then you do, we're doing at pi over 2, so we're going to do our derivatives, f upper n, that's the nth derivative, at pi over 2, and then we divide by n factorial, those are our coefficients, and then times x minus pi over 2, because this series is about pi over 2 to the nth power. So that's what we want to write out. So we have to find out the expression for these guys, the nth derivatives at pi over 2. So start writing out f of x is sine x, and then just start doing derivatives. See a pattern here. So f prime, derivative sine x is cosine x, f double prime, derivative of cosine is negative sine, f triple prime, derivative of negative sine is negative cosine, and then the fourth derivative, that's f upper 4 parentheses, derivative of negative cosine is sine x. So then you're back to the beginning, and then you just start cycling over again. And then you evaluate each one of those guys at pi over 2. So f at pi over 2 is going to be sine pi over 2, which is 1. That's a 2. And f prime at pi over 2 is cosine pi over 2, which is 0. And then f double prime at pi over 2 is negative sine pi over 2, which is a negative 1. And then f triple prime at pi over 2 excuse me, is cosine, well, I'm sorry, negative cosine pi over 2, but it wouldn't matter because that's still 0. And then it goes back to the 1, because this is sine x, so it would be sine pi over 2, which is a 1 again. So your pattern is 1, 0, negative 1, 0, 1, 0, negative 1, 0. So what we're seeing here then is that every other term is going to drop out. So let's just start writing out the terms here and see if we can find a pattern. So when n equals 0, the 0 derivative, that's the original term. So this is saying f upper 0 is just f at pi over 2. And then divide by 0 factorial is 1, and then x minus pi over 2 to the 0. So there's no power of x there. and then you are adding f prime at pi over 2. So if you plug in n equals 1 now, so it's f prime pi over 2 over 1 factorial. And then we do x minus pi over 2 to the first. And then n equals 2 is going to be f double prime at pi over 2. Over 2 factorial. And then x minus pi over 2 squared. And then we keep going here. So this will be plus f triple prime pi over 2 over 3 factorial, and then x minus pi over 2 cubed. And let's do one more, because then the repeating pattern starts. F upper 4 at pi over 2. And this is over 4 factorial. So I'm putting a 4 in here, and here, and here. So x minus pi over 2 to the 4th plus dot dot dot. Okay, and then our pattern of coefficients is 1, 0, negative 1, 0. So this is a 1, this is a 0, this is a negative 1, this is a 0, and then it starts again. This is a 1. So this is going to start out as a 1. The odd power term is going to drop out, minus 1 over 2 factorial, and x minus pi over 2 squared. And then plus, this is a 0, so this odd power term drops out, and then this is a 1, or I'm sorry, this is a 1 over 4 factorial, so then it's going to be plus 1 over 4 factorial, and then this will be x minus pi over 2 and 4th power, and then the fifth n equal 5 term is going to drop out, and then the n equals 6 term is going to return, and it's going to have a negative, so it would be minus 1 over 6 factorial, and then this will be x minus pi over 2 6th power, and plus dot dot dot. Okay, so we got this 1, negative 1, 1, negative 1, and it's going up in even powers. And now we want to try and write that in summation notation here. So this is going to be sum, and I'm not going to use n. I'm going to use a different variable here. Because our n is what we started with. So let me use k. And let's see here. So here I've got the 0 term, and then I've got the 2 term, and then I've got the 4 term and the 6 term. And this is when the number of the term is 1. This is when the number of the term is 2. This is when the number of the term is 3. This is when the number of the term is 4. So I want to, let's see. No, I'm starting at 0. I'm sorry. Get these off by 1. This is going to start at n equals 0 term. And you want to find the relationship between the term number and the general term. So this is the k equals 0, k equals 1, k equals 2, and k equals 3. And just notice some patterns here. So like the exponent here is double the 1, the exponent here is double the 2, the exponent here is double the 3, and the same with the factorial on the bottom, it's double the 3. So if we say this is summation from k equals 0, and we're going to go up to infinity, we're going to have a -1 power in there. So it's going to be -1. And let's see, this starts with a positive, and k starts with 0. So if we did -1 to the k, this would be k -1 to the 0, which is +1. And when k equals 1, we get here the k equal 1 term, we get -1 to the 1, which gives us a -1. So that's what we want there. And then underneath, we've got 2 factorial, 4 factorial, 6 factorial, which is twice the number of the term here, twice the 1, twice the 2, and twice the 3. So this will be divided by 2k parentheses factorial. And then their powers of x minus pi over 2. And then the pattern that we're noticing is that the power up here is twice the number of the term. 1, 2, 3. So this is going to be to the 2k power. And I just switched to a different variable. I just switched from n to k because here my n was hitting every my n was actually the value of the derivative here, and here every even derivative term dropped out. So I just decided to switch and use a different variable. You could use n if you wanted to still, that's fine. But I'm just trying to find a short form, summation notation form to write out this infinite series. So, and then so that was find the Taylor series. What are 2 applications of series expansions? So the reason that we do these series expansions is we can approximate complicated functions. So we could have these very difficult functions, and if we approximate them with a Taylor series or a power series, then this is essentially an infinite degree polynomial. If you FOIL this out, it's a polynomial. And number 2, we can use them to approximate solutions to differential equations. Okay, so we can solve differential equations. There's solution methods of differential equations that involve series. And you can use the whole series or sometimes part of the series. Depends on whether you want an approximate solution or an actual solution to the differential equation. Because remember, derivatives and integrals of these are real easy because you just do power rule on this part and your constants tag along for the ride. Alright, and then just another note here, also study your hour tests. So I'm going to kind of rotate the different problems. You know, these last 2 are going to be this type. You're going to have a power series and you're going to have a Taylor series. You know, pretty straightforward. And then the other ones, though, I mean, like the integration methods, you want to review the other integration methods that we had. So, you know, we saw a trig substitution and an integration by parts, but you also want to do, you know, partial fractions, you know, rationalizing U-substitution. And, well, we did see, you know, powers of trig functions. So, but you want to go back and, you know, and review those things. And then we did some derivatives in there that involved exponentials and logs. Also in that chapter we had, I believe, derivatives of the inverse trig functions and integrals of inverse trig functions. So you'll want to take a look over those because I may rotate the problems a little bit. So I'm not going to try and do anything that involves you having to memorize the formula. It's like the one integral that involved the secant integral ended up with integral of secant theta, and try to avoid all that. So but definitely, you know, go over the related problems on our exams. All right, very good.